to the third micro lecture about classification. As a recap for the previous micro lectures, we have discussed the different types of machine learning tasks, the stages of a typical supervised machine learning pipeline, how to do proper machine learning modeling, linear classification, and non-linear classification models. The learning outcomes for today is that you should be able, after this micro lecture, to choose the appropriate evaluation metric for the classification task, understand the probabilistic classification, measure the classification model reliability, and understand what is classifier calibration. Our agenda for today is that we are going to start with evaluation of classification models, what's confusion matrix, and then we'll move to probabilistic classification, measuring the model reliability and the calibration. So how do we evaluate our classification model? So let's say we have a model that can diagnose COVID. An infected person is a positive class, healthy person is the negative class. And we have a random sample of 100 persons. Two of them are infected and 98 are healthy. And we have here the different types of three different models for diagnosis of COVID. And we have here like the output predictions for the different models and different evaluation metrics that are calculated based on the predictions of these models. And as we can see here, the first model has an accuracy of 98% and a recall of 0%, precision undefined, and F1 score of 0%. The second one, 93% of accuracy, 95% of recall, and so on and so forth. So as you can see over here, if you are caring about the accuracy or the accuracy is the best evaluation metric for your task, you are going to choose the first model. If you are caring about recall, then perhaps you are going to choose the last model. So basically, according to the problems that you have and the business problem and the model outcome, you are going to have different values for different evaluation metrics, and you need to assess the model performance based on the evaluation metrics of interest. So basically, it's not only about the error rate or the accuracy. Accuracy and error rate are primary evaluation metrics that we are always considering. But accuracy, of course, is a proportion of correctly classified instances. Error rate is actually the 1 minus the accuracy. So basically, the formula for the accuracy is the normalized form for the this expression, which equals to 1 if the predicted class label is equal to the actual label, and it equals to 0 otherwise. But accuracy is usually not important. Actually, we have different evaluation metrics which we should consider for different business tasks. So let's have an example over here. We have a task for classifying between salmon and sea bass, which are like two different types of fish. And salmon is a positive class over here, sea bass is the negative class. Salmon is one of the tasty and fish that has like high cost or high price compared to sea bass. So basically, the cost of misclassifying a salmon as a sea bass, which is like a false negative by the end customer, will lead to having like the salmon fish in the can of a sea bass. And in this case, if the customer finds a tasty piece of salmon when he purchases a sea bass, he will not be like angry or will be like very happy of finding this tasty piece in the can of sea bass. And in this case, he actually can buy again another can of sea bass because he found it a salmon which is costly or has like a higher price. On the other hand, the cost of misclassifying a sea bass as a salmon, which is like a false positive, this means that he will find a piece of sea bass purchased at the price of salmon, so the customer would be very angry because in this case he paid like more money for buying the salmon can, and he found a sea bass which is more cheaper or cheaper than the salmon in this can. So in this case, he would be like angry. And so we just need to highlight in this business problem that the cost of false positive is much more than the cost of false negative from the model predictions. So we can actually, for any classification model, find out something called the confusion matrix. The confusion matrix for our task here, which is a binary classification task, can be plotted or written as follows. Here we have like on the rows the actual positive in the first row, the actual negative in second row. For multi-classification, we can like have the actual first class, actual second class, third class, and so on and so forth. We have here like in columns the predicted positive, predicted negative from the model predictions. And here for the intersections between these two columns, we have here the actual positive and predicted positive. So it means that it's actually like a true positive. For actual positive and predicted negative, it's false negative. For the actual negative predicted positive, it's false positive. For the actual negative predicted negative, it's false negative. And here we have the total number of instances. Here we have the total number of actual negatives, total number of actual positives, and here we have total predicted positive and total predicted negative. So this like an example over here for a model which has like 30 predicted positive and they were actually positives. So these are the true positive, 40 true negatives, 20 false negative, and 10 false positives. Participating at the end 400 instances, 50 actual negatives and 50 actual positives. In order to calculate the accuracy is the sum of true positive and true negatives over the total number of instances. Precision is actually the true positives normalized by the true positives with the false positives. So it's actually the percentage of true positives to the total number of predicted positives. The recall, on the other hand, is a relation or the ratio between true positives and over the true positive plus false negative, which is the ratio between true positives and the actual positives. So back to our example over here. So misclassifying a salmon as sea bass, which is a false negative, can be tolerated, but misclassifying a sea bass as a salmon, which is a false positive, cannot be tolerated. So in this case, we want to decrease the false positives as much as we can in order to decrease the false positive, which means that we need to care about the precision and increase the precision as much as we can. So if we have two confusion matrices over here for two different classification models, the first one has accuracy 88, precision 83, recall 50%. Second one has higher accuracy over here, 90%, precision 50, recall 100. Of course, in this business problem, we're going to choose the first model, which has lower accuracy, but of course it has much higher precision, which is the most important evaluation metric in our task over here. So this example highlights how we should consider selecting the most appropriate evaluation metric for our task. And here precision is the most appropriate one. So we need to select the first model, which has higher precision. Now let's move to another topic, which is probabilistic classification. So in some tasks, we should not only care about the predicted label, we should also care about the predicted confidence of the model or the predicted probability of the model. So let's say we have a machine learning model that can classify between images of cats and dogs, and it has 99% of accuracy. And we have here an input image for this cute dog, and we need to classify whether it's along the dog class or whether it's like a cat class. And basically here the machine learning model start to predict that this image could be like a cat more than a dog. But here for this prediction, it's just like getting the label would be like less informative than getting the probability that this image belongs to the cat class. Because if it has like low probability or low confidence, this means that the model is not confident of its prediction, and we can make like move this image to a human in order to double check the prediction of the machine learning model. So of course the model is still like 99% accurate, but in sensitive domains we cannot tolerate many wrong decisions, especially when the data distribution change. And in this case, probabilistic classification is needed. So when the model is not confident of its prediction or it has like low confidence level, low probability, in this case, we can move the instance to a human being in order to make double check on the AI model predictions. So instead of just predicting the label as dog or cat, we can have like for this image a prediction that this like zero point 0.7 like as a dog and zero point 0.3 as a cat. For this image, it could be like 0.95% as a dog. So the model here is pretty sure that this is a dog. For this image here, it could be like 0.45 as a dog and 0.55 as a cat. So this means that the model is not very certain or sure from confident from its prediction. And in this case, we cannot rely on the model prediction for this image. So probabilistic predictions can be retrieved for different types of classifiers. So let's say we have a linear model over here separating between these two different classes. Actually, we can predict probabilities instead of labels only. So in case of linear models, the probability could be the distance to the decision boundary for the instance of concern. And of course, in nonlinear models, we can also predict some probabilities. So in case of decision trees, we can predict over here the probability, which could be the percentage or the ratio of the positive class to the negative class at the leaf node that make the prediction. So here, let's say that an SUV car with a black wall tires it has like two positives and seven negatives. So actually, the percentage to be a positive class would be, or the probability to be a positive class would be 2 over 9 over all instances. So it would be like 0.22 probability to be as a positive class, and the remaining would be for the negative class. But how can we make sure that these actually predicted probabilities are reliable? Or are these predicted probabilities are actually calibrated so we can make sure that they match the confidence level of the model and we can rely on these predictions or not? In order to measure the reliability for a classification neural networks, we need to have something called reliability diagram, which measures if the model is calibrated or not. Calibrated means that the model predicted probability is matching its confidence level. So let's say we have an example over here for 1,000 of patients, input instances of 1,000 patients, and you are building a machine learning model that tries to diagnose if these patients are diagnosed with COVID or not. Then we found out that 90 of these 1,000 patients have actually predicted probability ranging from 0 to 0.1 as positives or as COVID diagnosed with COVID, averaging with 0.05 predicted probability. And we found out that 2% of those patients were actually COVID patients. So these actually the percentage of true labels out of these patients with 0 to 0.1 predicted probability. So now for an average predicted probability of 0.05, 2% only are actually COVID patients. Now for the next 110 patients, we have predicted probability from 0.1 to 0.2 with an average of 0.17. And we found out that 13 of those 110 patients, 13 percentage, were actually patients with COVID. So here for an average predicted probability of 0.17, 13 percentage were actually COVID patients, and so on and so forth for the different bins of predicted probabilities until we reach the bin for confidence level between predicted probability between 0.9 to 1. Then we start to make use of these values in order to plot the reliability diagram. These are two examples of two different models, the reliability diagrams of two different models, where we have on the x-axis the average predicted confidence levels bend over here. So here we have different bends for the average predicted confidence. And here we have over the y-axis, which is the average accuracy. And as we have like gaps between the average predicted confidence in each pin and the average accuracy in this pin, this means that the model is not calibrated. On the left, we have an example for an overconfident uncalibrated model where the predicted confidence levels are actually much higher than the accuracy, which means that the model is usually overconfident of its predictions. And here on the right hand, we have an example or a chart for underconfident reliability diagram, where there is the average model confidence for each pin is actually much less than the accuracy of the model, which means that the model is underconfident of its predictions. And here we have these gaps representing the underconfidence and these gaps representing the overconfidence. There is a process called the calibration of classification neural networks, which is actually a post-processing step to the model training, where we have the trained model as an input and we are trying to improve or map its predicted confidence level to another level in order to match the accuracy of these predictions. So here we have like an example for a reliability diagram for a classification neural network. And here we have like we can find the gaps between the average bin confidence and the average bin accuracy over here. And after applying the calibration step or the calibration algorithm over the trained model, you can find that these gaps are actually much smaller and the model becomes like better calibrated. In order to recap this lecture, we have covered different items related to the evaluation and the reliability of classification neural networks and how to calibrate it. You should be able now to choose the appropriate evaluation metric and think about the best evaluation metric that can assess the classification model. You should understand the probabilistic classification, measure the model reliability through the reliability diagram, and understand what is the classifier calibration step. As a hands-on and tutorial after this micro lecture, you are actually given a model that has an accuracy of 85%, but we should consider how much we can trust this model or how much is it reliable. Should we actually rely on these model predictions or should be cautious about the model predictions? We're actually going to evaluate this model, find out the accuracy, and find out different evaluation metrics like precision, recall, F1 score, and area under the curve. And in addition to that, we are going to find out the reliability diagram and calibrate this classifier in order to ensure that the probability estimates are more reliable as they seem. And by the end, you will be equipped by the knowledge to build not just accurate but trustworthy and reliable classification model. Thank you.